Study Box.
Hello, ladies and gentlemen. I'm Kazim Sayed, and I am a co-host for you at the moment. I welcome you all here at this wonderful webinar, which is all about maths. What is maths about, and why it's more important than more than what you think. We do have some really highly expert level speakers with us who will be joining us later on. Just to give you a little bit summary or a highlight of this today's webinar. So this webinar is all about exploring financial world of mathematics and its essential role in our lives. We will discuss how mathematics serves a powerful language, enabling us to do its modern day application in the field such as artificial intelligence, cryptocurrency. We will uncover the universal nature of mathematics and its incredible ability to help us around the world and around us. Uh, we will uh, we will dig into the concepts, deeper concepts of the mathematics and how it surrounds us. So I'm really thankful to our speaker, Professor Dr. David Hussein, who has joined us, my colleague Orhan Ghazi, who has joined us as well. So I'll hand it over to my colleague Orhan Ghazi for the introduction.
Professor Dr. David Hussein is currently working as the head of the Mathematics Department at Social Science and Soccer IBA University, Pakistan. Dr. Javid acquired his PhD degree from the University of York, United Kingdom, where he also took his master's degree in mathematical finance. Dr. Javid is a member of the London Mathematical Society, American Mathematical Society, and Pakistan Mathematical Society. He has taught at the University of York, United Kingdom, and at Soccer IBA University, Pakistan.
Thank you very much, Orhan. I again welcome Professor Dr. Javed Hussain for his valuable time, and I can imagine the difficulties and a busy schedule you might have. So we present you Professor Dr. Javed
Okay,
Hussain. Sorry.
so thank you, Kazim. Thank you very much for the invitation. And so when you spoke with me that you want me to give, a talk or a webinar on mathematics, I didn't knew much about who is going to be the audience actually, and so I thought that this is going to be kind of a general webinar, like it should be kind of accessible to the everyone, one who has a background in mathematics and like who doesn't have a background in mathematics actually. So during this talk, during this webinar, I'm gonna address. So my address here are going to be, because I can see you, it is going to be you and what do you call Arhan actually, okay? And I hope that in this talk I'll try to give you a sense in a pretty much non-technical way. I'll probably not go too much deep into the mathematics, but pretty much in a non-technical way, that what the mathematics is all about, and and why this way of thinking really matters actually. So like why I mean, so we all have kind of right from the beginning of the schools actually, when we started learning things for the first time, like this maths was there. And I'm sure that when the Kazim is like doing his PhD, so like some kind of mathematics he must be encountering, at least say statistics, for making the quantitative conclusions actually. Anyway, so why this maths is important, and why, and what it is all about actually. So that's what is going to be my intentions in this talk. I hope you all can see my screen. So let's get to the things. We all have memories with the maths. Okay, so if I say, for example, meet with a random person and say one of my colleague, say one of my student, one of my you know elder, and ask from him that what do you think of maths actually. So the kind of reaction that they have goes something like this actually. That the people have this kind of mostly a sore reaction with maths actually, and then there are reasons for it actually. Okay, so later on I'm going to even explain in a sense that how there's a hidden mathematics even in this simple GIF actually. Okay, so if I collect the views that what the maths is all about, so I hope that I'm gonna get something like something like answers something like this actually. That okay, it's like it's hard and it's all about graphing and it's about variables and x and y and z and you have numbers and fractions and you want to solve things and you know so like people give you what you call the different experiences of maths actually. So that's one way. It's like a pretty much vague picture that what maths is all about. So I want to give you kind of at least the essence of what the mathematics is all about in this webinar actually, and try to convince you with that. I just make a quick Google search, and I said that okay, let's see that what Google is saying. So then so when I made that search, it turns out that um, the maths is all about formulas and equations, and maths is all about you know some kind of silly things, bunch of symbols making no sense. That's what the maths is actually. And what usually people perceive of say mathematicians that what's going on in their head actually. So what they do, so maybe they just think that there are a bunch of equations floating around in their heads, and they are just trying to solve the problems in their head. So that's what the picture that uh, that you that usually, for example, a common person has in his head actually. That maybe these nerdy people, they just play with their symbols, and they, all the time they're writing things, writing the symbols for no reasons and making computations and so on and so forth. So I want to try to take away all of these myths and try to give some basic essence of it. So Einstein said something interesting actually. He said that the most incomprehensible thing about the universe is that it is comprehensible actually. That's a, certainly it's a deep question that you know we say that that we are trying to understand the universe, we are trying to understand things around us, um, but there is an implicit assumption that the things are understandable actually. It's like why the universe is understandable at first place actually. So it's like a deep philosophical questions on which like there could be lots of discussion, but I want to focus on this word, something called comprehensible actually. That what do you mean by when we say that the universe is comprehensible? So how do we comprehend things actually? So the way to I hope that you'd agree with me that the way to comprehend things, or the meaning of comprehensible, the way to comprehend things is to what do you call use your common sense and uh, like observe things through the senses and try to describe things in the terms of language actually. So we write things, we write words, and then we try to describe things through those words. So the first we try to comprehend things through our senses, through common sense, and then we try to what do you call uh, describe usually things in a language actually. Um, but the question is common sense enough actually? So it's like okay, I mean, why we need something else other than our common sense actually? And you have tons of languages. So why you need another language, so-called language, the language of mathematics actually? So you have Turkish, and you have Urdu and Sindhi and Punjabi and English. So if you have these language, why these languages are not kind of uh, capable of, or what's wrong with them actually. Are they good? Are they not good enough? So I'm going to try to convince you that the common sense is not enough. Your senses are not enough to comprehend things, especially universe, things that are going in markets, the things that are going around you in all sort of all sort of manners. And the languages, the common language, that you and me speak is also is not enough actually. So what are some of the troubles with, say, for example, common sense? Here a video. Let me just share this video and say, Kazim, please let me know that whether if you are able to listen to this video. Are you able to listen to this video? Kazim, can you hear me? Are you able to listen to this video?
No.
No, okay, you're not able to listen to this video. So let me just try to do something. Or let me just try to go to another example actually. So maybe that would be something useful. So um, so here's an example. Forget about what is written on the left and left hand side of your screen that you're seeing. So let's take a circle actually. So you have a circle, and so I hope you all can see circle. And then let's take, for example, a point, and that this point is just moving left to right. I hope that you agree that you're just seeing that a point is moving left to right. And then, for example, I take another point that is moving, for example, sideways, but on a straight line. Say I take another point that is moving on what do you call a straight line. So all of these points are moving on a straight line actually, in certain directions. So let's say that I'm taking some more bunch of points that are just moving on a straight line. And say, for example, if I keep on putting some of the points, okay, what you will see that, all of these points, each one of these points is moving on a straight line, but your senses are being tricked actually, and you are kind of looking at the, your senses is telling you that there is a circle that is moving within this circle actually. Okay, so it's like your senses are being fooled. So when you're going to see, for example, this circle, okay, and then that these points, none of these points is moving in a circle actually. So if you closely look at each of the points, that each one of these points are moving on a straight line, but when you put them together, it turns out that your senses are telling you, your senses are being fooled in a sense that um, that they are they are like these points are moving in circle, which is not there. They're not moving in circles actually. So this common sense, is really is not enough actually. So let me for a moment, let me just try to say, okay. So that was the first example. So I wish I could make you hear this video, but let's just get to another situation actually. So if I put a glass right in front of you, and like the normal glass, and I ask from you, which is greater, the height of the glass, in other words, that how high the glass is, or the circumference of the glass actually. So what do you think? What would be your answer actually? So Kazim, what would be your response to this? What do you think? What are you gonna say? Is the height is bigger than the circumference?
Yeah,
This round
that's
thing
what
on the
it's
table,
yeah, that's what it seems. Height looks like
greater than.
obviously glass. Yeah, yeah, yeah. Glass
Okay,
looks
so that
longer.
looks obvious. That's what your common sense is telling you. But here's a little experiment actually. Just take a thread, for example. Just take what you call a tape, and try to measure the height of the circle, and try to measure the circumference of this height of this glass and the circumference of this glass, and you will always find that the circumference is greater than the height actually. Okay? So if you take a normal glass or any pot actually, you will find that the circumference is always bigger than what do you call the height, actually, unless you're talking about a straw, actually. So a straw is not a glass, actually. Okay, so I'm talking about a simple glass. So your common sense is telling you that your senses are telling you the height is bigger, but in reality the circumference of a glass is bigger, actually. So I can quote lots of such examples where your senses and what you see with your eyes, they really what do you call are not enough to correctly understand the thing, actually. So you can't trust your senses always. Okay, I'm not saying that leave common sense at all, but I'm saying that you know you always should have an element of a skepticism, what do you call, um, within the when you're trying to draw conclusions based on common sense, actually. So the common sense is not enough. Now, okay, so how about the language, actually? How about the language? I mean, language is also something that is troublemaking. So, say for example, consider the first sentence, actually. So if I say that I always say a lie, so I always tell a lie. So So, Kazim, if I ask from you that, when I'm saying that I always say the lie, do you see a trouble with this sentence, actually?
Yeah, obviously, like normally people won't say that I am lying. Normally
Okay.
they would say he is lying or she is lying. So I find
Okay.
it, yeah, like
Okay. So
quite
that's
unusual.
one thing. That's one thing. But
Yeah,
the other thing is that when I'm saying that I always lie, and I'm making this statement, actually. So let's imagine that I'm saying that I always lie, and that this statement is true. That means that whatever sentences are coming out of my mouth is a lie.
yeah,
And I'm making this statement that I always lie. The question is this statement itself true? So if it is true, it must be false, actually. Think about
yeah,
it. So when I say that I always lie, so how can you trust my this sentence that I always lie? Because maybe I'm lying, you know, while I'm making this sentence, actually. So really the language is really what do you call is a bit troublemaking, actually. I mean, you could create sentences for which you can't say with a clarity that what do you call whatever I'm saying is true or false, actually. So let me give you another example. Okay, so I say I saw a woman with a telescope, actually. So what do you think of this sentence? Do you see something funny about this sentence, actually? It seems like a normal sentence.
yeah. Seems like normal.
Okay, seems like normal. Okay,
Yeah,
so can you can you okay? So here's something funny, actually. So if I say I saw and I put a comma and then it's a woman with a telescope, actually. So I put a comma after the saw. So I saw a woman with a telescope. So that's one sense that you can get out of the sentence, actually,
yeah,
right? That there was a woman with a telescope and I saw her.
yeah,
Okay. What the other, what do you call meaning you can get out of this sentence? That I saw a woman with a telescope, actually. So in other words, I'm carrying the telescope, and with that telescope, I saw the woman, actually. Are you getting the point? So the two senses can get out, what do you call, of the same sentence, actually. So what does this show? That the language sometimes becomes ambiguous. Language sometimes become unclear, actually. Okay, and now, if you're trying to understand things that they exist around you purely based on the common sense, are your senses, and then you're trying to express those what do you call observations in the terms of this English language, are just writing essays about things. So sometimes these the language is inadequate. It's not enough to what do you call clearly describe what do you call or comprehend the things correctly, actually. So I hope you agree with me. I hope You got the essence of my thing that I wanted to say, Kazim. Is it good?
Yeah, yeah, definitely.
Okay, so the common sense, troublemaking. Language sometimes can become, what do you call troublemaking too. So the question is, can I trust my, what do you call common sense is? You have to be careful. You know, when I try to explain things using some language, you have to be careful because the language can give the, what do you call, language can be troublemaking sometimes actually. So what do I want to convince you now is that how the mathematics is a language, and it's a language. It's a way to comprehend the things and to describe the things in such a way that where there is no ambiguity, you know where there is no, what do you call that, the troubles that we saw previously. Okay, so in other words, you can simply replace or if you accompany the your common sense with mathematics, and then you say things out in the language of mathematics, then you're saying things perfectly. You're saying things in a way which are kind of which are kind of clear actually, without ambiguity. And you can trust on those, what do you call, things that are being said in the terms of mathematical language. Now you quite often hear that the mathematics is a language, but how it is a language actually? I mean, let me just try to illustrate this and allude to this point and get back to maybe my one activity, and that would kind of elude me to well, that is going to kind of elude you to the how mathematics is a language actually. So what is the role of a language? So you make observation and you write essays actually. So for common people, you make observation and you write a essay, and that bunch of letters and that bunch of words, okay, that you try to, what do you call, put together, describe a real world situation. So you made an observation, okay, you made an observation, you saw something, you went through a journey, and then you write that journey in the sense of, what you call, these words and letters actually. So therefore you call that words and letters as the language. Now I'm going to show you, or I'm going to try to convince you that when you try to write things in, what do you call, in mathematical terms, you're precisely doing the same thing actually. So what you can do, you can take a real world situation and you can describe it in the terms of symbols, in the terms of mathematics actually. All right. So yeah, so let's get into that. So on your screen, what you are seeing at the moment, I just want that you treat yourself as an artist actually. So just treat yourself as, what do you call, someone. So forget about this graph and what is written on here and what is written on here and what is numbers. So just treat this, what do you call, this straight, this white part as your whiteboard, as your canvas actually, in which you can draw anything. So I can do what I can draw anything I like actually on that canvas actually. So just treat this thing, this white part as a canvas actually. So what I'm going to do now is that I'm going to draw something. Okay, I'm going to draw something on this canvas, and then something will happen here. Okay, so let's say, for example, I'm drawing a line. So let's say that I drawn a line, and I'm and that's the mathematical world. So that's a canvas, that's a mathematical world. So in my mathematical world, I just drawn a line. And then I want to see that what does this line mean in, what do you call, practical terms actually. So what will happen is that what do you call, a turtle will appear. Okay, and that the turtle is kind of moving actually. Okay, and the turtle is moving. So in other words, this line for me, on this canvas is equivalent that the turtle is moving and trying to cross this beach actually. So if I, for example, draw another line, okay, and this time say I make this line a little bit more inclined actually. Okay, so my previous line was like that. Okay, like which is kind of less inclined, and then like this line is making a bigger incline. Okay, so keep in with I'm not telling you this mathematically. So I'm just telling you, just treat this as a white paper, and you are drawing the bunch of lines on that white paper actually. And now what will happen is that, what do you call, the two turtles are appearing, okay? And, the one turtle is going slow and the word turtle is going, what do you call, fast actually. And Kazim, if I ask from you, what do you think, which turtle, which line is kind of representing the fast going turtle actually? So what do you think? What would be your answer actually to that? So this the line with the less incline, a line with the more incline.
I think more inclined, the one that looks more
Yes.
vertical, yeah.
Good, good,
And it's
good, good.
longer as well.
It's longer as well, actually. Okay. So line with the more incline, yes, I can see that is going to what do you call, um, the make the turtle run quickly actually. Okay, so if I make it more inclined, so the turtle is going to even more what do you call, move faster. So it's like if I have to kind of um, make the turtle move fast, I have to make my line in this canvas, okay, more inclined. And if I want to make the turtle move really slow, I need to make it what you call less inclined. And you can see that now, the turtle is following, trying to follow this line, but now it is moving really, really, really slowly actually. Okay, so that's one of the things. Now, what do you think? If I ask from you, Kazim, that I want now that turtle should stop. It shouldn't move at all, actually. So, what do you think? What kind of line should I draw that can represent that the turtle is not moving at all?
I think it should be completely horizontal, like touching the
Good, good.
baseline.
I'm amazed. What do you call, Kazim? That
Thank
you're good at maths. So see, a turtle appeared, but the turtle is not moving at all. Turtle is not moving at all actually. Now, for example, now I want my turtle to move backward actually. So like the turtle is moving forward, like going from down to up actually. So what if I want my turtle to move down actually? So I need to draw, for example, something like this. I hope that you agree with it. And now you see that the turtle it appears and it's like trying to move the back way. Okay, it's like try to move the back way. All right? Try to move the back. Now, let me give you, for example, a journey. Okay, so imagine that I want my turtle to move a little bit. Okay, and then I want my turtle to, for example, um, stay there for some time. Okay, so it's like it just moves and then stays wherever it is. So like it's just stop moving for some time and then it moves back actually. Okay, so the question is, for this journey, can I draw a bunch of line? Okay, a bunch of what do you call, a bunch of lines that represents that journey. So what I can do, I want my turtle to move. Okay, so this will make my turtle to move, and then I want, say for example, my turtle to not move at all for some time, and then I want my turtle to move back actually. And let's see that whether this happens or not. Okay, the turtle is moving and then it is stopped, and then now what do you call, the turtle is moving back. So now I hope that you agree with me, what do you call, Kazim, that if you give me any journey, the way turtle is moving, I can just draw a bunch of lines on this canvas, and the turtle is going to do whatever I have drawn here. Actually,
Yeah,
it's going to move accordingly. Okay, so it's
yeah,
like I can encapsulate, I can write the journey of the turtle rather than in words, okay, but just drawing bunch of lines actually, just drawing bunch of lines. So I hope you agree with me.
yeah, yeah.
So I can describe the entire journey by a bunch of lines. So these bunch of lines are telling you. So for example, if I ask from you to, I don't know, Kazim, if I draw this curve, and if I ask from you, what do you think? What turtle is going to do? Let me redraw it. Okay, so redraw it. Okay, what do you think? What's your prediction actually? What journey turtle would make while like following this, say, bunch of according to this what do you call
Yeah, I
these
think
two bunch
the
of lines?
turtle would start moving, and it would start moving quite fast,
Uh
and then
huh.
it would come back. It would return.
It will return, and it will
Yeah,
return a bit slower actually.
yeah,
So let's see. Let's see. So it's moving fast and then coming slow. So see, you are spot on actually.
yeah.
You're spot on. So isn't that interesting actually? So here's the thing actually. So isn't that fascinating that I just draw some bunch of lines and that bunch of line correspond to a journey, a real world journey actually. Okay, and you can give me a journey and I can just draw a bunch of lines here, and you'll see that the turtle is going to follow, move according to those bunch of lines actually. So let me just draw one last thing and then move to move back to slides. So for example, imagine yourself being a turtle. Say the turtle wants to cross a road actually. So imagine you are a turtle and you want to cross a road, and on that road there are lots of cars. What do you call? There's a lots of traffic actually, and so sometimes you move forward and sometimes you move backward. So if you want to say, for example, um, draw a curve, how does that curve look like? So I hope you agree with me that curve should look like something like this actually. Okay, so I hope you agree with me that curve should look like, so it's like going, so it's like you're moving forward, going, coming back, moving forward, coming back, moving forward, coming back, moving forward, coming back, and so on and so forth. The question is, you know, is the turtle is going to do that? And you see that that maybe the turtle is trying to, what do you call, um, cross a road, and there is a heavy traffic accident. So see, the each curve is kind of representing a journey, and every journey can be represented by just drawing some bunch of lines at it. So in that sense, it's a language. And then I would say, so here's the thing actually, later on. This is not just about turtle. Now say a cousin that replace the turtle, say by a price of a stock that you're interested in, that you have bought actually. Then so it's like your price is going up and down. So it's like I can interpret this, what do you call, these bunch of lines, I don't want to call them graph, that I can interpret that, aha, so like now the turtle, if I replace that turtle with, what do you call, a stock, then I can say that, okay, so what does this graph means, that the stock price is just going up and down. Okay, the stock price is going up and down. Okay, so for example, if I draw something like this, okay, and I say that, okay, replace in your head now the turtle by, what do you call, by the revenue, for example, the profits that, say for example, your say a shop is making, a superstore is making actually. Okay, so what does this curve is going to represent in the terms of revenues actually. So now your revenue is turtle. Okay, so like your revenue is moving the way turtle is moving actually. Okay, so it's like your revenues gradually. So you open the shop in the morning, then your revenues went up for some time, reached to a maximum point, and then the revenues started going down actually for that superstore. Okay, and that's how. So like this turtle is really an abstract thing. You can replace it with almost any kind of thing actually, and then you can describe the motion of that thing by, what do you call, just drawing some bunch of lines onto, what do you call, this canvas actually. And it turns out that almost everything in the universe, like these planets and stars and the life and the way life is evolving, the way economical markets are working, the way everything is changing. Actually, they all are, they all could be described. Their journeys could be described. Their movements could be described through these bunch of lines. Actually, okay. So these bunch of what do you call graphs. Actually. So I hope that you can say that, I can treat this graph as a language actually.
Yeah,
These
definitely.
bunch of graphs is a language. I hope that you agree with me that it's a language. It's just
Yeah,
telling you in a
definitely.
story. Correct?
Yeah, definitely.
So maths is a language actually. So in that sense, maths is a, what do you call language. So I hope that you are a little bit convinced actually. So let's move on. Let's move on. I can show you more stuff, but okay, I don't know, how much time do I have? Okay, but okay. So how maths is a language? So I hope that it's concerned. So what do you call what the mathematics was all about actually. So so mathematics is all about studying the patterns actually, and the patterns. So if I ask from you, what would be the simplest? I mean, it's really difficult to define, kind of give an all-encompassing, what do you call encompassing definition of mathematics. But you know, but at a really non-technical level, if I ask from you, or if someone asks from me, what the mathematics is all about, mathematics is all about studying the patterns. Actually. And you see that, and I'm going to show you some examples that the patterns are everywhere. So it's all about studying the patterns. Okay, so that's what we do. So whenever you see a mathematician is working in its what you call office, okay, is kind of trying to study some kind of patterns actually. Okay, so how do we study the patterns? So so it's like, what is the job of a mathematician? So what mathematicians do in their offices? Okay, so I know that a biologist is doing something practical, a surgeon is doing something practical, a physicist is doing something practical, but what mathematicians are doing in their offices? So when they are, say for example, so what they are doing, so so the first thing is that when you try to study patterns, you need to notice patterns. So patterns are all around uh, your. You see that things repeat themselves. You see that things are changing. What do you call? Things are following some kind of pattern. So we notice patterns, and then we describe patterns actually. So when I'm saying that maths is a language, so it's language to do what? It's language to describe patterns. So that's how we what do you call we could interpret that. Mathematics is a language, but language of doing what? Patterns that emerge, you know, anywhere. You can just describe them in the terms of what do you call mathematics. And then what we do, then we try to what do you call generalize those patterns actually. So not only describe the patterns, then generalize, because the generalizations, when you generalize a pattern, it just make you, so based on that you can make predictions actually. Okay, so like from that generalization you can have all sort of interesting conclusions. So let's just start with an example actually. So here's a kid, so who is having a bite of, say for example, a lemon, and he's giving this reaction actually. Okay, so say this kid is a kind of I don't know, so it's some European kid, maybe some Turkish kid, and giving you this reaction. Okay, so how about say a blonde kid actually? So with the blonde kid, which for example someone from Europe actually would give you a similar kind of reaction, the answer is yes actually. Okay, so you observe the pattern. And then how about an Asian kid? So the Asian kid is eating the lemon, so having a bite of a lemon and giving you the same kind of reaction. And then say for example a South Asian kid actually. So is it going to give the same kind of reaction? The answer is yes actually. So what do you see? You see a pattern. And what is that pattern? The pattern is that when the kids, say for example, are having a bite of what do you call lemon, they all kind of give almost a similar kind of reaction actually. Okay, so we notice those patterns, we kind of try to describe that pattern, and I can generalize it. And by generalizing, I can say that if you take any kid from anywhere in what you call in the world, and if you give it a what you call a bite of a lemon, its reaction is going to be this actually. Okay, so we notice the patterns. So the pattern in reacting, like how the kids are, for example, reacting, on lemon bite, and then generalizing it. Okay, describe it and then generalize it actually. So that's what precisely we try to do when we are, so for example, encountering things in different kind of songs. It's not really different than what I just said here actually. So here's an example of it. So if I give you, for example, a bunch of numbers and it goes like 2, 4, 6. So um, so do you notice a pattern actually, cousin?
Yeah, I think it's like even numbers.
Yes, it's like even numbers. You notice a pattern. So what you just did is that you not only noticed a pattern, but you also described the pattern actually. Okay, describe the pattern. But okay, so one thing that I can say that okay, it's like what is the pattern? The pattern is that if you pick this previous number and add, say for example, 2 into it, you're gonna get the next number, and you take add 2 into the 4, you're gonna get 6, and so on and so forth. Okay, so it's like I observed a pattern, and then I described it in just saying by words that this sequence, like every term in this sequence goes up by 2 actually. So that if and I can do what I can write this to get the next number, like you need to add 2 actually. Okay, so it's like I can describe it. So you observe it, and then I describe what you call the patterns, and then we can generalize them actually. We can say that aha, so I can say that the nth term in this sequence is a multiple of what you call 2. So in other words, if you think about the first term, so it's 2 times 1. So you take the second term, it's 2 times 2, and you take the third term, it's 2 times 3, so on and so forth. So you generalize this, what do you call, patterns. And essentially, frankly speaking, that's all what mathematicians, what do you call, do. So it's not just about numbers, but we do this for all kind of interesting things actually. So for example, here is something that you see that here, you're seeing a video of what do you call, a process of a mitosis in which say a cell is splitting into the multiple cells actually. Okay, so what we are seeing is that these are bunch of the cells, and these bunch of cells are being splitting into what do you call multiple cells. The question is, can I kind of observe these pattern and make sense of it? Can I describe these patterns mathematically? Um, so one who is interested in, say for example, studying the patterns in biology, would be interested in describing what do you call these kind of patterns actually. So say, so for example, one way to describe it is that, okay, imagine you have a parent cell or maybe a pair of cells, and the pair of cells after some time produce another pair of cells. Okay, and then they got then now you have two pair of cells, and the two pair of cells again becomes what you call more and more pair of cells. So it's like you just see that the 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 number of cells is being increasing actually at each unit of time actually. So it's like describing the patterns in biology. Okay, I'm trying not to be too much technical. I could, speak in more technical terms, but as I'm saying that my primary audience is Kazim and Irhan, so I would like to convince them that basically. So the patterns are there in biology, and we as a mathematician, okay, so we are interested in understanding those patterns and describing them mathematically, and then make predictions about those patterns in future. Okay, so here's another, say for example, um, uh, example actually. So we know that we have things like cell in our body. Okay, and in body you have a nucleus, and in nucleus you have what you call, at the very basic level, you have something called DNA. And a DNA is, if you really see, it's like it has this double structure, double helix structure. But it's, I mean, if you really see, it's nothing. It's just a, you can just treat it as that. It's a long piece of thread put together in a small, what do you call, nucleus of the cell actually. And this is really an actual picture of, what do you call, a thread actually, uh, thread of, what do you call, DNA. And then, you know, I hope that you agree with me that when you try to put a long thread, a bunch of long thread in a really tight small place, what can happen is that those threads can get entangled actually. Okay, they can get entangled, and we say that when the DNA get entangled, we say that the person has a disease actually. So the person is now sick. Okay, and now we have something in our bodies. It's called our immune system. Like it's an army of enzymes. So what they want to do, so what they do, if they see that the DNA in a particular cell, say for example, a bunch of cells is entangled, so they just roughly go there and try to get rid of that entanglement actually. Okay, that try to get rid of that knot actually, that that say for example, knot in the DNA actually. Okay, so they try to unknot that knot. Okay, the enzymes. And then if we say that, okay, the, your enzyme is not able to, say for example, unknot those knots, then you can say that's a kind of a permanent disease now, a permanent something that you can't cure, like HIV or like AIDS or something like that. Okay, so there's an entire branch of mathematics called knot theory. Okay, and what knot theorists do, they do nothing. They just, their work is just to, what do you call, how to take the different kind of knots and how to resolve those knots. Can we kind of understand those knots? Can we unknot those knots actually? And what do you call, if, and what is happening these days, like these mathematicians, what they are actually trying to do is that they are learning these, that how to unknot these knots. And then what we can do is that we can basically this unknotting procedures roughly, we can teach these unknotting procedures, okay, you know to the enzymes, the army of the enzymes that we have actually. Okay, when you kind of put a vaccine, for example, for a certain disease into the body, you are exposing, you're teaching the, what do you call, you're teaching the, what do you call, your army of enzymes, your immune system, that how to respond against that particular disease actually. Okay, so we do not. That's what mathematicians do, and we try to show that how doing those knots and unknots is a pretty useful business actually. So here's another example. Imagine you take a metallic plate actually, and then you sprinkle some grains of salt on it, and then you expose that, what do you call, uh, the plate of what do you call, that metallic grain to the different frequencies of vibrations actually. Okay, I can show you different examples. So what will happen is that when you expose this metallic plate on which you have a sprinkled, what do you call, salt, the salt, and you expose it to what you call different kind of vibrations, the salt is going to take naturally different shapes actually. And there are lots of such experiments in which, say for example, you give, say you play a violin actually, and then the salt will take the different shapes. You play a piano around it, and you play some other instrument, it takes the different shapes. So whenever you expose the metallic plate to different level of frequency of vibrations, and it would give you different kind of patterns emerging very naturally, without making any without any involvement actually. The pattern emerges actually. So these patterns are there actually. Okay, and there is, what do you call, entire branch in what we call mathematics, those who study such kind of vibrations and who study such kind of patterns actually that emerge very naturally in a variety of the contexts. So that we are captivated, you know. So we are grounded. We are, we are living in a universe. We are living in a place where the patterns are everywhere, and the task of mathematicians is to study those patterns, to write those patterns in the language of mathematics, the language of graphs, and the bunch of lines that I told you, and then make generalizations, make predictions based on that. So here's another other example. Okay, it's a beautiful, sweet example that whenever you see a flower, actually, so you'll observe something in strange actually, and you can go out and see this in your garden actually. So when you go out, you're gonna see that your flower always have either a one petal, okay, or it's gonna have two petal, or three petals, or five petals, or eight petals, or 13, or 21, or 34 petals. You know, you will not probably find a flower with, say, four petals, actually. You will not find a flower with six petals and seven petals. You find it, you're going to say there is something wrong with this flower. So the flowers naturally follow what you call, um, you know, this sequence of numbers actually. And you see that, is there a pattern in this sequence of numbers? This sequence of numbers, it's called a beautiful sequence called a Fibonacci sequence, and you get this sequence by what do you call, it's like you get the new term in the sequence by adding the previous two terms actually. So you take 2 and 1, you add 2 plus 1 equal to 3, and then 3 plus 2 equal to 5, and then 5 plus 3 equal to 18, and 13 plus 18 is 21, and so on and so forth actually. Okay, so you have this, this simple sequence of numbers, but it appears what do you call naturally in, say, for example, flowers actually. Now you ask a interesting question. I mean, why the flowers are following the petals and the flowers following this sequence actually? Why they are just appear in these numbers actually? And once you observe this, and then some of the kind of mathematical answers have been found about this phenomena, is that it, like, why the what do you call, the flowers are following, for example, this particular sequence. So one of the reason is that if you have a small place where you want to pack what do you call, more and more stuff actually, then what could be the so the number of things that you can pack within what you call a small place actually. Okay, then that number should be a term in what you call a Fibonacci sequence, and that's precisely what the flowers are trying to do. So within their available small space, they want to grow, but they want to grow in such a way, in such a tight manner, that they grow maximally, but within that limited space actually that they have. Okay, so they naturally choose what do you call, these like a term in this sequence actually. So therefore, you will have the flowers that have one petal and two petals and three and five petals actually. Kazim, you want to say something?
Yeah, actually, we will be
I'm just
closing.
finishing. I'm
Yeah,
just finishing.
yeah.
I'm
Thank
just
you.
finishing. I'm just finishing. So you see patterns in what do you call, galaxy? Like, okay, like you have day and night, and the things are moving around the sun. The entire galaxy is moving, so on and so forth. You see patterns in astronomer actually. I mean, once I asked from one of my elder actually that, I mean, what if you don't have any watch, and you want to know the time really in the middle of the night, then how would you know the time? So then I'm going to see the stars actually, because the stars that they are appearing on sky, they are not just randomly appearing actually. They have patterns, and those patterns could be studied. And like astronomy is the entire area that you try to study the patterns appearing in the skies, in heavens, using mathematics actually. Okay, so here is something, a little thing actually that, okay, I think this would be a little bit aside actually. So let's leave it. Let's leave this slide for now. And thank you. And that's it from my side actually.
Well, thank you very much, Dr. Javed Hussain. It was really a pleasure listening to you, and I really appreciate how easy you made it to understand. Normally, mathematics is quite difficult, or at
Thank you.
least people presume, but the way you explained, it's really wonderful. I'm really thankful to you for your time and effort, and hope to see you again. Thank you.
Thank you. Thank you very much.
Thank you.
Thank you.
Study Box.